Here we're going to link the forces that are acting in simple harmonic motion with this spring in the block to some other values. Whenever this block is stretched any distance or compressed any distance away, the spring force is going to be equal to kx. And the spring force always acts opposite the applied force. So if the block was pulled to the right, the spring force would be acting to the left. And then if we release the block, that spring force is going to cause the mass to accelerate in the direction of the spring force. So that means these two are equal to each other. And from the prior equations, we find that the acceleration of simple harmonic motion is going to be equal to that omega squared x. If we substitute that in, those go away, and we can solve this for, forgot my negative sign here, which makes a negative sign here, which makes those cancel out. So that omega squared is equal to k over m. We also know that omega is equal to 2 pi over the period. So if we substitute this in to that equation, we get this relationship, and if we want to solve for the period, so we have to square root both sides. Then flip everything. Move 2 pi over to the other side as well. So that the period is equal to 2 pi times the square root of m over k. And again, k is that spring constant. Now, let's think about this conceptually. If I have the same mass but attached to two different springs, and if one of them has a higher spring constant, how will that affect the period? So the larger the spring constant, which means the stiffer the spring, also up here means the greater the force. Greater the force, greater the rate of change in velocity, you would think that the period should drop. If we look at the mass, if we had the same spring but put on two different masses, so if we increase the mass, what's going to happen to the period? The period should go up. All right, so think of that mass taking longer to accelerate. So it would be tougher to move from one location to another, and it would take, of course, more time. So you can reason out what goes where in this equation. And you're going to see this form where the period is equal to 2 pi times the square root of a series of variables over different types of simple harmonic motion situations. In order to understand those situations, we have to look at this situation in a little different way. So we're still starting with the same type of equation, same exact equation, where the force equals k times x and the force is equal to ma. So the negative signs cancel out. Now what we're going to do is we're going to write this in a differential equation form with respect to x. So if we integrate a, we get v, integrate v, we get x. So working backwards, a is the second order derivative of x. And there's a few different ways to note the derivatives. You've seen it as the ddt, but when it's the second order, you have the squares there. Another way to do it is write it as x of t prime. So this is, if it's the second order, you do x double prime of t. The last way is the dot method. So you can say x dot, or for here, it'll be x double dot for the second order derivative of x. Doesn't matter which way we write it. So here we have m times the second order derivative with respect to time of x, and that's going to equal kx. Now we want to get this alone, so we have to divide by m. So and all we're doing here is getting a form of a differential equation, and the important part of this is this factor right here and how it's organized. If we look at the previous equation, we found that this value was omega squared. And then we square rooted each side and use the fact that omega is equal to 2 pi over the period. All right, so substitute this in here and solve for the period, and then we got that the period is equal to 2 pi times the square root of m over k. And I told you that we're going to see this form over and over again. And you can see that whatever this factor is in that differential equation is the opposite that goes into that period equation. So the purpose of going through this is to relate the last proof for the period to this differential equation form. So now we're going to look at another situation and relate the differential equation to this one. And I'll do that in the next video. And that video will be called the small angle approximation.